Welcome to a session on application of van der Waals equation. We will see how far the van der Waals equation is applicable to real gases. Let us move on to the topic. Topics dealt with this application of van der Waals equation to real gases. We will be seeing what are the units of van der Waals constants, that is A and V, and we will also see what are the significance of the constants A and V. Now, let us go for the application of van der Waals equation. Now, we all know that the van der Waals equation is P plus A by V square into V minus B is equal to RT. This is for 1 mole. Okay. Now, what I am going to do is, I am going to open the bracket, that is I am going to multiply P with V, I will get the first term PV, then I am going to multiply P with B, so that makes P into minus B, that is minus PB, plus A by V square, I will put it as like this, into V. Now, V square and this V get cancelled, and next is A by V square into minus B. So, that will be minus of AB by V square is equal to RT. Hope it is clear. Now, what I am going to do is, I am going to retain PV on the left hand side, and I am going to take all these terms to the right hand side. So, here it will be PV is equal to RT is already there, minus PB, when it goes to the other side it becomes plus PB, plus A by V, when it goes to the other side it becomes minus A by V. Now, minus AB by V square, when it goes to the other side it becomes plus AB by V square. Now, this is the form of the equation. When I have expanded the brackets, I get this as PV is equal to RT plus PB minus A by V plus AB by V square. Now, we are going to consider the condition when the pressure is low. It is not very low, but a low pressure. The expression is PV is equal to RT plus PB minus A by V plus AB by V square. Now, what happens when pressure is low? Volume will be high. If volume is high means I can neglect this term. Why this term? Because V is a very small number and squaring that makes it more small, and when it comes to the denominator, this whole value, this is in the denominator, the whole value becomes very small because V is in the denominator and I am going to square it too. So, dividing that you can neglect this term. Again, when volume is very high, there is one more thing, the co-volume can be neglected. So, that term neglected, or I can consider that to be 0. So, this term also you can remove from this. I will explain it. When pressure is low, volume is very high. When volume is very high, this term AB by V square is neglected because V is very high, square in the denominator. So, this term is very small. Again, when volume is very high, we need not consider the molecular volume of the molecules. So, I can neglect that this term too, I am neglecting. Finally, I will get the expression as PV is equal to RT minus A by V. Remember, in the previous session, we have seen that when we draw a graph, that is PV against P, it has been found that in certain cases the curve is having a dip. Okay, that is at low pressures. At high pressures, you can see that it keeps on increasing. Now, this is the reason for that. That is, PV will be less than RT. PV is equal to RT is the condition for the ideal gas. It will be less than, and that is the reason in which the graphs were showing a lower value than the expected value, which is equal to RT at low pressures. Okay. So, that explains why there is a dip in the graphs when the pressure is low. Now, what happens when pressure is high? Again, I will have to take this expression PV is equal to RT plus PB minus A by V plus AB by V square. Now, here the pressure is high. Pressure is high means volume is low. You cannot neglect anything, either you cannot neglect this B, because when the volume is small, volume of the molecules cannot be neglected. But we have two terms, that is A by V and AB by V square. When V is small, okay, and this is a minus term, you can neglect this term. Okay. And similarly, when V is small, we are going to neglect this term too, which is in the denominator. So, finally, what we have is RT plus PB, that is at high pressures. Now, at high pressures, you can see in this graph, when the pressure increases at a higher pressures, there is an increase from the value, that is, it is greater than RT. That explains the rising part in the plots. Okay. So, the reason, in the other case it was minus A by V, that is, it will be lesser than RT. In this case, RT plus PV, because pressure is high, and therefore, what we have is we can explain the rising part of the real gases in the plots we have obtained. Next, we are going to consider very low pressure. Again, I am going to, very low pressure means volume is extremely high. Volume is very high, or it is very low, it is extremely high. Now, one more point is, we do not have the term, I will write the expression once more, that is here PV is equal to RT plus PB minus A by V plus AB by V square. Now, volume is very high, P is very low. So, this term can be neglected, this can be neglected, this can be, all these three can be neglected when volume is extremely high. Now, what we have is PV is equal to RT. We can explain this, because when at very low pressures, the gas will be occupying very large volume, in which molecules will be far apart. Now, when the molecules are far apart, there is no neglecting the intermolecular force of attraction. You can neglect, because the molecules are far apart, there is no intermolecular force of attraction. Now, when the volume is very high also, the volume of the molecules can be neglected. So, both the cases are possible now, and in that cases we have PV is equal to RT, that is at very low pressure. Okay. Now, let us consider the temperature to be very high. Temperature is very high. Again, the same effect, volume is very large. Again, the pressure correction and volume corrections both can be neglected. because molecules will be moving with very high energy or kinetic energy or velocity you can say, and here in this case volume also is very large, both there will not be any correction for pressure or volume. Again under these conditions you can have PV is equal to RT, and this is a combined effect we were saying about, that is at low pressures and high temperatures, combining both two. When pressure is low and temperature is high, gases tend to be ideal. Okay. Now, let us see the exceptional behavior of hydrogen and helium. We know that when we plotted PVP, PV against P, okay, and this was for the ideal gas. Now, for hydrogen and helium, we did not find any dip. Both moving up, only the rising portion, they did not have a dip. Now, what is the reason for that? Now, again I will have to put this equation, PV is equal to RT plus PV minus A by V plus AB by V square, I suppose. RT plus A by V plus A by V square. Okay. So, this is the expression. Now, what is A? A is for intermolecular forces of attraction. Okay. B is for the volume of the molecules. Now, when hydrogen and helium, when we consider these two, they come first in the periodic table with atomic numbers very small, and therefore their size is very small. They have got a very small size, and when the size is small, their attractive forces also will be small. Also will be very small. There will not be much because very small size, weight is less, mass is less, and their attractive force is also very less. Volume of the molecules also is very less. Okay. In that case, the attractive forces, we are having the term A by V, right. So, any term including A, that is a pressure correction terms A by V in these two terms, which involves the pressure correction terms A by V. In both cases, that can be neglected because very small size, okay, there is no much attractive forces between them, and these two terms, that is A by V as well as AB by V square, can also be neglected, in which both involve the pressure correction term, which is for the intermolecular force of attraction. Now, when we neglect both these, the final equation will be PV is equal to RT plus PV. PV equals RT plus PV. That is, in most cases, the value of PV will be greater than RT, and that is why hydrogen and helium shows only the rising portion in normal temperatures. When the temperature is lowered, of course, it shows a dip also. But in normal temperatures, here PV is equal to RT plus PV, that means it is something greater than expected value, and therefore, for hydrogen and helium, it always shows a increasing portion. Next is units of van der Waals constant, which I have just mentioned it. Here we will be seeing the units both in SI as well as CJ system. Now, the pressure correction term must have the same units as pressure because there is additive pressure, which we have already discussed, which is equal to A n square by V square. A n square is small square meter raised to 3, which is equal to n m raised to minus 2, and unit of A will be equal to n m raised to minus 2 into m raised to 6 whole divided by mole square. And finally, you will have newtons meter raised to 4 mole raised to minus 2, and in pascals it will be meter raised to the power 6, because 1 pascal is equal to newton meter raised to minus 2 mole raised to minus 2. Now, let us see what is in the CGS system. In CGS units, A n square by V square should be equal to atmospheres, which is the unit of pressure. Now, A mole square divided by liter square is equal to atmospheres. Okay. Now, unit of A will be equal to, I will have to take the mole square to the other side. It becomes mole square in the denominator, liter square will go to the numerator, liter square, and that will be equal to atmosphere liter square mole raised to minus 2. See, that is what is given here. Now, you know that 1 liter is equal to 1 decimeter cube. Substituting that, liter square means decimeter cube square, and that makes it as decimeter raised to 6. So, atmosphere decimeter raised to 6 mole raised to minus 2. Now, unit of B, the volume correction term must have the same unit as volume, otherwise we cannot subtract it, V minus NB. To subtract that, both this should have the same units. So, NB is equal to meter cube in SI units. So, mole into B is equal to meter cube, or unit of B is equal to meter cube. This goes to the denominator. So, I can put it as mole raised to minus 1. Again, in CGS unit, NB is equal to L in that is liters. In CGS unit, mole into, mole is for N, into B is equal to liter, and unit of B will be equal to liter divided by mole, or liter mole raised to minus 3, and liter I can put it as either decimeter cube, then it becomes decimeter cube raised to mole raised to minus 1. Next, let us see what are the significance of van der Waals constants A and B. So far we have been seeing that actually van der Waals equation, we have been introducing A as a proportionality constant and B as just a correction for volume which has to be applied for volume of the molecules. Now, let us see what are the significance. The value of A of a gas is a measure of intermolecular forces of attraction present within the gas. So, intermolecular force of attraction, it gives us a measure of intermolecular. So, if A is large, if A is greater means intermolecular forces greater. So, it has got a very strong attraction between the molecules. Okay. If the molecules they attract very strongly, it is easier for them to get liquefied, because just applying a small pressure and a small decrease in temperature, the gas gets liquefied. For example, if I take carbon dioxide or ammonia, they get liquefied fast just because they have got stronger intermolecular force of attraction. That is the reason. So, the value of A is a measure of intermolecular force of attraction, and greater the value of A, stronger is the intermolecular forces of attraction present in it, and greater is the ease of its liquefaction. So, if A is large, that gas will be easily liquefiable. If A is smaller value means it is not easily liquefied. For example, A for hydrogen and helium is low, and also mostly for nitrogen too, but in olden days hydrogen, helium and all were considered as permanent gases, that is they can never be liquefied. That is because their value of A is very small, which means that the molecular size is small, as we have seen in the previous discussion. the size is small, intermolecular attraction is small, and therefore they cannot be easily liquefied. We have to give drastic conditions like very low temperatures and very high pressures to liquefy hydrogen and helium. Now, let us consider the constant B. This is for the actual volume of the molecules, that is excluded volume, or you can say that incompressible volume, or it is also known as co-volume. Now, this is the volume of the molecules. Now, if volume of the molecules is less, means that is the size of the molecules will be small. If the volume of B is large, means the size of the molecule is greater, because that is why they require more space to occupy. So, the effective volume B is 4 times the actual volume of all the molecules in 1 mole of a gas. The derivation we will be seeing it later, but effective volume B or the co-volume B, it is actually 4 times the actual volume of 1 mole of a gas. And larger the value of B for a gas indicates larger volume of the gas molecule and thus larger size of the molecule. The molecular size will be very large. Now, here there are the values of A and B. See, for hydrogen it is 0.244, the value of A. It is very small. You can just check with other gases. This is for hydrogen. Okay. Now, let us check for helium. See, helium also it has got a very small value, and these two gases, since this is very small, their intramolecular force of attraction is less, and therefore, we have already explained it. It has got only a rising part in the PVP, PVP plots. Okay, this is because their air values are extremely small. For nitrogen it is 1.39, for oxygen it is 1.36, for chlorine it is 6.49, for carbon dioxide 3.59, for ammonia it is 4.17. So, these gases you can liquefy first. See, chlorine can be liquefied, carbon dioxide can be liquefied, ammonia can be liquefied. The value of B suggests the size. From here we will get an idea of the size of the molecule. Here we are getting an idea about intermolecular attractions. Okay. Now, here you can see that hydrogen is 0.0266, it is very small in size. Okay. Nitrogen is slightly larger, oxygen is also okay. When we come to helium, again it is 0.0236. See, this is very small gases, hydrogen and helium. Out of this, ammonia is 0.03, carbon dioxide is somewhat larger, chlorine is somewhat larger. Larger the size, they will be requiring more volume to occupy. Okay, that is about the significance of A and B. Now, to conclude, we have been seeing application of van der Waals equation to real gases. Now, let us go through it once more. For the real gases, we have considered many conditions like low pressures, high pressures. Low pressures, we have seen that PV is equal to RT minus A by V, which shows that the value of PV will be always less than the expected value of RT, and that explains the dip of the curves in PVP plots. Not only in that, in the instead of PV we have taken even said, in that also we could find it, that is compressibility factor, in that also you can see the same thing. Now, at low pressures, it is moderate low pressures, not very low pressures. In that case, PV is equal to less than RT, that is RT minus A by V. Now, at high reason I have already explained, that is when the volume is high, these two terms are neglected, and that is the reason we have a dip in the curve. At high pressures, again these two terms volume is very small and these two terms are neglected, and finally we will have the equation as PV is equal to RT plus PV, that is as the pressure increases. Now, when pressure is increasing, what will happen? That is, the value of PV keeps on increasing, and that explains the rising part in the PVP plots. Okay. At very low pressures, that is extremely low pressures, the volume will be extremely high, and as a result all these, this P is small, PV can be neglected, volume A by V, AB by V square, all these get neglected, and finally the equation takes the form PV is equal to RT, where the gases tend to be ideal. Again, at high temperatures, very high temperatures, you can neglect both pressure as well as volume corrections, because volume is very high and no intermolecular forces of attraction. So, these two conditions we have, that is, when we combine pressure to be very low and temperature to be very high. At high temperatures, again here volume corrections are neglected and we have PV is equal to RT, that is again the ideal condition, and combining these two, that is low pressure and high temperature. Do not forget that at low pressures and high temperatures, gases tend to behave ideal because volume is very high, volume of the molecules can be neglected, no intermolecular force of attraction, the pressure correction also can be neglected, and we have the equation as PV is equal to RT. Next is the exceptional behavior of hydrogen and helium. They show always a rise at normal pressures and temperatures, and you can see that from the expression, that is the term A by V and AB by V square can be neglected, because due to the small size of hydrogen and helium, you have the value of A to be very small, or A small means size is small. When size is small, the attractive forces are also very small, and as a result these corrections can be neglected, that is A by V and AB by V square. Finally, we have PV is equal to RT plus PB, which shows that in most of the conditions, that is most of the temperature conditions, until unless we go to very low temperatures, we have only the rising part, that is always PV will be greater than RT. Okay. So, always they show a increase in the or rising part in the equation. Next, we have found the units of A and B, which we have discussed it in earlier session too. And finally, the significance of van der Waals constants A and B. A stands for intermolecular force of attraction, measure of intermolecular force of attraction, and B stands for the volume of the molecules, which gives us an idea about the size of the molecules. And just going through the values of A and B, you can see how the molecules intermolecular force of attraction, in which case it is stronger and which case it is lower, and also we get an idea about the size of the molecules of the gases. So, that is all for this session. I conclude. Thank you.